So, all right, getting us ready for this here quiz tomorrow. Couple of things to make note of. If you're using one of the calculators in class, this is going to be fun because my regular Algebra 2s are now doing everything in radians. So more than likely, if you're using one of the calculators in here, you're going to want to go into mode and make sure you're back into degree. I'll especially warn that for tomorrow because I don't want you getting a bunch of wrong answers because, well, you're not in the right mode. That would be awful. So let's see here. I think I got to change mine too, to be perfectly honest. Yep. Back into degree mode. We won't be in degree mode much longer, though. Sorry, let me get that cleared out. So we have got ourselves a basketball player standing outside on a sunny day. Okay. He is exactly 6 feet tall. I am not going to attempt to draw him. He is just going to be a stick. If he casts a 7.8 foot shadow, what is the angle of elevation of the sun? Okay, couple of things to make mention of. Your shadow, when you see them, are actually on the ground. So we want to make sure the 7.8 is on the ground, not on our hypotenuse. The other thing I want to make sure of is when you're thinking about an angle of elevation, you're looking at an angle that's going upward. Okay? This would not be an angle of elevation up here. So I'm looking for the angle that's formed right there between the ground and the top of this basketball player's head, which is forming this shadow. So, a couple things to watch out for. First, which trig function are we going to be using? I thought I heard it. Tangent, because I have opposite and I have adjacent. The other thing you'll want to be careful of is that, again, you're looking for an angle. That's why I put the -1 in there to remind me, oh yeah, when I'm punching this in, I need an inverse. That's how I get the angles. And again, typically with these, if you don't see something otherwise, we're always going to tenths on sides, degrees, whatever it happens to be. So 37.6 degrees looks like a good plane to me. And that's how we'd work this. Now this is the one that gets people every time, so I'm hoping if we really are specific, we're going to have this one go well. From the top of the school, you spot your car at an angle of depression of 41 degrees. If your eyes, whoa. Okay, are exactly 78 meters up, how far away is the car from you? Okay. We're 78 meters up. An angle of depression would actually not even be inside my triangle, at least not the initial angle. But we remember our alternate interior angles to know that the 41 degrees will end up down here. You're like, wait a minute, that's the same place that the angle of elevation was. Right. So no matter if you see angle of elevation or depression, that's where your reference is going to end up being. So that makes life pretty easy. So if your eyes are up here, so we're up here, there we are. How far away is your car that's down here? If it had said we're sitting at the bottom of the school, we'd have had an x value here, but I'm up here, so there's my distance that I am away. So what sides am I working with, or what function do I need? Okay, opposite and hypotenuse, so we need sine. So the sine of 41 is opposite over hypotenuse. Be careful, because a lot of them that we did when we were working through here had the hypotenuse value, and so we had this value, we just multiply and we'd be good. But remember, that's not the way this works. I'm going to have to multiply both sides by the x to get that out of there, and then of course, since I'm solving for x, I've got to divide by the sine of 41. But no second this time because I'm not looking for an angle measure. I'm looking for a distance. So it looks like about 118.9 would be a reasonable answer. And that's the other thing you want to watch with these. Is my answer reasonable? If that had been 78 and I'd have gotten like 2,000 as my answer, that wouldn't be reasonable. So I'd want to go back and check something and see what the heck's going on with that. All right, we got us a parallelogram. Lengths of 18 and 27. I'm just going to go ahead and label them all here. And one angle is 38. Okay, before we go any further, sometimes your eye can let you see something pretty acutely. So here, I can notice this angle looks obtuse, this looks acute. Make the assumption that would be my one angle is 38. Also doesn't hurt for me to see that's the short side where it would also be found. Find the length of the longer diagonal, which would be along here. But if this is 38, that's being cut with this. So what I actually want to know is the angle that's being trapped in here. Any ideas on how to figure out what this angle is?
180 minus 39.
Perfect. Okay, they're supplementary. So I'm going to take 180 minus the angle I have here, the 38. And I find out that obtuse angle is hanging out up there is 142. That's what I'm going to use. Why are you going to use that? Because I'm trying to find the length of the diagonal. I have two sides and their included angle, and I'm trying to find the side that corresponds to that angle. Use the law of cosines. Okay. So I'm looking for this side, and when I'm doing that, I take the sum of the squares, and again, this is on your sheet, minus 2 times their product, times the cosine of my given angle. And this is the one that I can actually type the whole thing into the calculator right off the bat. It's not the one where I'm having to take it in pieces and be careful. So, let me get this typed in, make sure I typed it in right. Now again, be cautious, because that's not my solution. I need to know what x is. So don't forget to square root whatever you get. And again, this is about being sensible. If the two other lengths were 18 and 27, I wouldn't think it would make sense for the diagonal to be 1,119. 42.6, yeah, that's reasonable. And I can make sure I'm good with that. Drawing my angles. Handy dandy little protractor again here. Now, am I going to be looking for within like 1 degree on these things tomorrow? It's not going to look for perfection, but if you're like 5 or 10 degrees off, yeah, I'm going to mark that. So when I'm doing these, remember, we're going counterclockwise for my positive degree angles. And I just start working my way around the axes until I notice my next axis would be too much. Going to 270 is too much. I need to go from this 180 and add another 85 to it. But here's the kicker. Whichever axis you stopped on, that's the axis we're going to line up with. And since my angle is going to be below the x-axis, my protractor is going to open up below the x-axis. So I'll scooch this over a little so we can see maybe. So 70, 80, here's my 85 about right here. Just kind of hover there. This is going to be a really narrow angle, but we're going to make this work. And then I always make sure I finish my curve with my arrow to explain here's where I started, here's where I ended, and I'm going clockwise. Excuse me, counterclockwise with it. Oh, if I went clockwise, I have to mark myself off. So that's how that would work. If it's in radians, in other words, if it's in pi, you can make yourself a quick math note to see what it would be in degrees. Because remember, what's pi in degrees? I'll stop typing. 180. So I can just do 7 times 180 and divide it by 4. So this is really a 315 degree angle. So I'd say, okay, I'm good till I get around to 270, but then I need another 45. I ended on the y-axis. My angle's going to open to the right. Line up with the y-axis. Get my 45. And finish her off. So again, be cautious. And the only other really anything that you have to be cautious with is making sure when it's a negative, that you're going clockwise instead of counter. So when you leave from your initial side, which will still be here on the positive x-axis side, you start going the other direction. You're like, okay, so negative 270, ended on the y-axis. My terminal side is going to be up here, though, to the right. So line up with the y-axis. Look for your 10 degrees, which is right here. Whoops, let's redo that. Get that finished off and we're okay. And then the same thing we did for number 5 we can do for number 7, except it's a negative. 2 times 180 would be 360. Divided by 3 means we're looking for a negative 120 degree angle. We're good till 90. Ending on the y-axis, opening to the left for another 30. Hooray, hooray. So again, as long as you're pretty close, you're fine, but if you like switch up and you say, instead of line up with the y-axis, you line up with x, you end up 15 degrees off, that's the only way I can really think you're going to get whacked at all in there. Conversions, radians to degrees, or degrees to radians. Again, when we're going degrees to radians, the pi goes on top. Reduce it all the way down. Don't leave it as 140 pi over 180. Okay, we want to simplify because it's going to start getting us in good habits for the unit circle here coming. So pi over 180. And simplify. And the easiest way to remember, of course, besides knowing you should have pi when you're going to radians, is when you're going the other way, we need the pi in the denominator, so the pi's cancel. Seems reasonable. And 540 divided by 4 is 135. Pi's canceled. 900 divided by 3 is 300, and we're looking good. Any big issues on the front here before we go flipping over to the back and doing a little more application type stuff? Like, no, not awful so far. Not awful for a Monday. All right, a positive and a negative coterminal angle for each. Again, positive, we're going to add 360 degrees. negative, we're going to subtract 360. But the final answers, remember, have to end up positive, of course, for a positive and negative for a negative. So if they don't, you have to keep doing it. So like for positive here, no big deal. I add 360 to 245. I get it, I'm good. If I subtract 360 from 245, I get a negative degree measure. That's good. I'm happy. 13 is where the problems can start, though. The adding part doesn't give me a problem. Okay, that gives me 1140. But the negative, be careful. Because if you subtract 360 from this, you end up at 420, but that's not negative yet. So that's no good. So I'm going to subtract 360 again. I end up at 60 degrees. It's still positive. That's no good. When you finally make it to a negative degree measure, now you're good. And the same thing would go if I started with a negative and I added 360 and it was still negative. The same idea is going to apply here. Only other thing I got in this section, if I could write this in like 125 font, I would. Start in radians, end in radians. If for some reason, because I'm not even going to do this to even let you think about it, if for some reason you turn this back into degrees and try to mess with it, you better get it back into radians for your answer, or I'll like flip my lid. So here, remember, 360 degrees is the same thing as 2 pi, or subtracting 2 pi. And we talked before about when I'm trying to add or subtract, it's really not that big of a thing, because all I'm going to do is take whatever's in the denominator times 2 pi. So 4 times 2 pi for my plus would be negative 3 pi over 4 plus 8 pi over 4. 2 pi times 4. Which works out for me because it comes out positive. When we go the other way, it's going to work out nice for me as well. I'm just going to subtract it, and I end up with a negative value, which works. And I'm good. So again, nothing too terribly awful here. Now, reference angles. If you remember looking at that little chart that had the plus and minus 180 and all that, that works. But here's the easiest way to remember. How do I get to the nearest x-axis? Kind of do a picture in your mind of what these are going to look like. If you need to sketch yourself a quick picture, that's not even a bad idea. Because you may sit here and go, okay, 195, let's see. So it'd be 90, 180. Oh, from 180, that little bit more here, that's what I'm going to be looking for. Well, if it's the nearest is 180, because that's the nearest x-axis, that's how I find my reference angle. They will never be negative. You never go to the nearest y-axis. If I'm at 110, you're like 110, okay? That's like here. Nearest x-axis, 180. So 180 minus 110, 70. Closest to get me, whether it's 0, 360, 180. It's always going to be one of those that gets me the closest. So then, thank you. Yep. So 348, and I'm thinking again, I'm like 348, that's like way around to here. Closest, 360. You're like, wait a minute, I'm noticing something else. They're never going to be over 90 degrees, are they? No. Because no matter what quadrant you're in, you're always within at most 90 degrees away from the x-axis in one way or another. Now again, if you see something in radians and it spooks you, okay, nothing terrible. You can stay in radians, or if you do go to degrees, 5 times 180, let's see, it'd be 900 divided by 6 is 150. You're like, okay, 150. Closest would be 180. So 180 minus 150 is 30. Be careful, you circle 30 degrees. Oh, I'll be writing radians in big, huge red letters across there. This needs to go back. If you're going to go this route, no, I'm thinking ahead. Times pi over 180 to get back into radians. Start radians, end radians. I don't care if there's a little bit of conversion in the middle, but ooh, there better be conversion. I'm just saying. Okay. Negative 7 pi over 4, same deal. If you wanted to, if you're like, yeah, I'm a little more comfortable doing these with some degree measures. For now, that's okay. We'll get you to a point that it's a little more. Okay, so this is really negative 315. So I'm like, okay, what's that mean? 90, 180, 270. 315, closest is going to get me to 360. 360 minus 315 is 45. Don't leave it as 45. Convert it back. .45 in radian mode, which you will again be just know off the top of your head here very soon. It's pi over 4. And we're happy, at least for a moment. Now a few apps and we'll be happy ready to go here. All right, minute hand of a clock. Minute hand is 7.5 inches long. How far did the end of the minute hand travel from 9 a.m. to 11 a.m.? Use the formula S equals radius times theta. Okay, questions here. All right. How many hours did this wonderful clock spin around? 2 hours. Okay. So I know a few things. I know my radius is 7.5 inches. I also know that a circle does a complete revolution in the minute hand in 1 hour. So I know 1 hour is 360 degrees. What is that in pi speak, in radian speak? 360 degrees in radian speak. 2 pi. So 2 hours would be 4 pi. So 4 pi times 7.5 looks like it went about 30 pi inches. And if it drives some of you crazy to try to speak that way because you don't normally, and you want to go into decimal mode and say it's 94.2 inches, that's fine. Because I know we don't normally go around telling people things like that. But I'll take either. I'm perfectly content speaking either language. I am multi-mathlingual. All right. Terminal side of theta in standard position contains the following point. Find the exact values for the 6 trig functions. This is my x and my y, otherwise known to us as adjacent and opposite. -3, -2. All that does for us is tell us where our reference angle is. Because our reference angle will always make contact with the origin. It tells me my x value is -3, my y value is -2. So basically it's just helping me get the drawing. I don't know the hypotenuse yet though. So I need to use the Pythagorean theorem to find it. Make sure, if you're doing this with a calculator and not in your brain, that you are using parentheses around each of these because your hypotenuse will never be negative. You should get the square root of 13, which isn't going to break down because negative 3 squared is 9 and negative 2 squared is 4. 9 and 4 gets me the 13. And then I can just start running with this. So for instance, my sine, here's my reference angle, is opposite over hypotenuse, but remember, I'm going to have to rationalize that, but I'll come back to it. Cosine, negative 3 over the square root of 13. Tangent is opposite over adjacent, which would be 2/3. And the reason, again, I haven't changed these yet, because now I can just take them and flip them over and notice the only two I have to fix are sine and cosine, which won't take long because I'm just going to multiply the numerator and denominator by the square root of 13. And when I do that in the denominator, it gets rid of the radical, and I'm happy. And the other 4 are all okay, which is why I didn't fix those until the end. Because otherwise I'd have had to fix this again. Who wants to do all that? That's no fun. So that's how that would work. This will always help me to figure out what quadrant I'm going to be in with my drawing. That's why that's there for me. And we talked a little bit about where each of my functions are positive. All of them. All right, so we're told the tangent is positive. Where's the terminal side? Tangent is positive. That's even enough. Because again, those are the ones that we know where the quadrants are going to be positive. So you're kind of killing 2 birds with 1 stone on this. Now if you put 1 and 4, I'd want some sort of an 1 and 3. Whew. I'd want some sort of an explanation, but if you draw the picture with it, hey, I'm good. Because that tells me where they're going to be positive, and that's what this is telling me. All right, last one. Find the area of a triangular shaped piece of land with sides of 60 meters, 40 meters, and 35 meters. Okay. Oh, let's see, 60, 35, 40. Okay. You're like, ooh, all sides. Yes. So I'm going to be looking, because I'm going to need an angle to be able to get my area. So remember, when we're using the law of cosines with 3 sides, use the biggest one. And then again, we've got our formulas for these. So it'll be our biggest side squared equals the sum of our other 2 sides squared minus 2 times their products. So some of you are like, ooh, I need to find that formula sheet. That could come in handy on this. Times the cosine of what we're looking for. So we're trying to find this angle right now to help us. Be careful, because this is the one where I have to treat this part differently than I treat this one, because it's almost like having a variable term. So I look, I'm like, okay, so 40 squared plus 35 squared. And I want to take that away from the 3600 because I'm going to want to move that to the other side anyway. Okay, so let's just do this. 775 equals, and then we'll multiply these guys together. And I will slow my roll here in a second. Okay, so what I've done is I squared the 40 squared plus 35 squared and subtracted it to the other side where the 60 squared is at. That's where the 775 is coming from. And then I went ahead and multiplied these, and now I've just got to go ahead and divide through. So we got 775 divided by negative 2800, And again, it's an angle, so make sure you're using second when you're doing cosine. And just little things, like remembering the negatives there. Oh no, I don't want another parenthesis. Bless you. Now, unfortunately, I'm not done. That got me an angle that I needed to be able to find the area, but that's only the first part. So if this is 106.1, now I take, to find the area, 1/2. The two sides that trap my angle in, multiply those, times the sine of the included angle. And this we can put in all at once. So 0.5, 35, 40, sine of 106.1. What did you all get? You're gonna see. I'm gonna see if I can get the same thing I do. Oh, gee, what did you all get? I've got it on the screen. That's awesome. He. Okay, that was kind of funny. So we are. Oops, wrong button. Okay, so that's basically what you'll be looking at for tomorrow. Now, one other thing I just wanted to make mention of, and actually I'm going to